Welcome. In this video, we're going to do an example where we are given a vector field, capital F, which is conservative, and we're asked to find the potential function, which is going to be little f. So the vector field, F, is equal to y sine zi plus x sine zj plus xy cosine zk. So we know a couple of things. One thing is that the gradient of f equals the vector field f. So the gradient of my potential function is equal to that conservative vector field. So that means that each of these components represent the partial derivatives of little f, or rather, partial little f with respect to x is equal to y sine z. Partial f with respect to y equals x sine z. And partial f with respect to z equals xy cosine z. Now to find that potential function, I'm going to start with any one of these three. I like to start with f with respect to x. So we're going to integrate, then differentiate with respect to y, then integrate with respect to y, then differentiate with respect to z, and finally integrate with respect to z. So I like to work through them in order. It just kind of helps me keep track. So little f is equal to the integral of partial f respect to x integrated with respect to x, or rather the integral of y sine z with respect to x. So that means f equals, I don't have any x's there, so that y sine z is a constant, and I have xy sine z. So integrating, I then need to write my plus c. But in this situation, that c value is some function, I'll call it g, a function of y and z. We've only dealt with x, so we're left with y and z here. Next, we're going to find this partial with respect to y. So partial f with respect to y. Now differentiating with respect to y, that means x sine z was a coefficient. So I have x sine z, and then I have the derivative of g, which I'm going to write partial g with respect to y. Of course, we were given partial f with respect to y up here. So now I can say that x sine z equals x sine z plus partial g with respect to y. Simplifying this, I'm going to see that partial g respect to y is equal to 0. Now, if you integrate 0, if I integrate that partial g respect to y with respect to y, the integral of 0 gives us a constant. And of course, we haven't dealt with z yet, so this constant could be a function of z. So when I integrated this derivative, I got that original function. So g is equal to h of z. So now I can come up here and I plug h of z in. This leaves me with f equals xy sine of z plus h of z. So I did my differentiation and integration with respect to y. We just do this one more time with respect to z. So partial f with respect to z. X and y are constants. The derivative of sine is cosine z. So I have xy cosine z plus h prime of z, or rather partial h, partial z. Now, partial f partial z is xy cosine z. So I'm going to come down here. I'm going to plug that in. Xy cosine z equals xy cosine z plus dh dz. Those guys cancel, and we have partial h with respect to z equals 0. So what that means now is that my h of z function is the integral of this partial h with respect to z dz. Integrating 0 is going to give us a constant. And since I've already integrated and dealt with the potential for having a variable in y and a variable in z, I can just call this c. And that means that h of z is equal to c, and my f of xy z equals xy sine z plus that c value. So xy sine z plus h of z, which we just found, is c. And again, you can check this. If I take the partial with respect to x, with respect to y, with respect to z, I should end up with these three partial derivative component functions. So that is how we deal with finding a potential function in 3 variables. As always, email me with any comments, questions, or concerns.